Section 1 Introduction. Let's dive into the world of autoregressive models, specifically large transformers. These models have proven to be more capable than their smaller counterparts, as demonstrated by models like GPT-3, Lambda, Party, and PaLM. However, there's a catch. Decoding a single step from these larger models takes significantly more time than from smaller ones. And to make matters worse, these steps are done one after the other, meaning decoding K tokens requires K serial runs of the model. Given the importance of these large autoregressive models, several strategies have been developed to speed up their inference process. Some methods aim to reduce the inference cost for all inputs equally, while others focus on the fact that not all inference steps are created equal. Some steps require a large model, while others can be approximated well by more efficient models. These adaptive computation methods aim to use fewer computational resources for easier inference steps. However, these solutions often require changes to the model architecture, alterations to the training procedure, and retraining of the models. They also don't maintain identical outputs. This is where our work comes in. We've observed that inference from large models is often not limited by arithmetic operations, but rather by memory bandwidth and communication. So, we propose increasing concurrency as a complementary approach to using an adaptive amount of computation. Our solution? Speculative execution. This is a common optimization technique in processors where a task is performed in parallel to checking if it's actually needed. The benefit is increased concurrency. A well-known example of speculative execution is branch prediction. For this to work, we need an efficient way to suggest tasks that are likely to be needed. In this study, we extend speculative execution to the stochastic setting, where a task might be needed with some probability. We apply this to decoding from autoregressive models like transformers. We sample generations from more efficient approximation models as speculative prefixes for the slower target models. With a new sampling method, speculative sampling, we maximize the probability of these speculative tasks being accepted, while ensuring that the outputs from our system have the same distribution as those from the target model alone. For instance, a sentence consisting of 38 tokens was generated by our method with only 9 serial runs of a larger target model, thanks to a smaller and more efficient approximation model. The probability of generating it remains unchanged. We've tested our method on a variety of tasks and model sizes, and compared actual wall times for T5XXL to those of the robust T5X implementation. The result? An out-of-the-box latency improvement of 2x-3x, without any change to the outputs. Our method is easy to implement in actual production settings, doesn't require training new models, and doesn't change the outputs. Therefore, in situations where memory bandwidth is the bottleneck, and compute resources are available, it may be a good default to accelerate sampling from autoregressive models like transformers. In summary, our main contributions are 1. An extension of speculative execution to the stochastic setting, with a new sampling method we call speculative sampling, and 2. A decoding mechanism we call speculative decoding that can speed up decoding from autoregressive models, without any change to the model architectures, training regimes, and output distributions. Now, let's delve into the specifics of speculative decoding. Let's denote the target model as M_P, from which we're trying to speed up inference, and P, X_T, X_T, as the distribution we get from the model for a prefix X_T. Let's denote a more efficient approximation model for the same task as M_Q, and Q, X_T, X_T, as the distribution we get from the model for a prefix X_T. The core idea is to use the more efficient model M_Q to generate a certain number of completions, then use the target model M_P to evaluate all of the guesses and their respective probabilities from M_Q in parallel. We accept all those that can lead to an identical distribution, and sample an additional token from an adjusted distribution to fix the first one that was rejected, or to add an additional one if they are all accepted. This way, each parallel run of the target model M_P will produce at least one new token, but it can potentially generate many new tokens, depending on how well M_Q approximates M_P. Section Summary. In this section, the authors discuss the challenges of decoding from large autoregressive models and propose a method called speculative decoding to accelerate the inference process. Speculative execution, a technique commonly used in processors, is generalized to the stochastic setting, where a task might be needed with some probability. By sampling generations from a more efficient approximation model as speculative prefixes for the slower target model, the authors are able to increase concurrency and accelerate inference without changing the model architectures, training procedures, or output distributions. Their method achieves significant speed improvements without sacrificing the quality of the model outputs. Section 2.2 Standardized Sampling. Let's delve into the concepts of standardized and speculative sampling, and how they relate to the generation of tokens in a model. 2.2 Standardized Sampling. There are numerous ways to sample data, such as argmax, top K, nucleus, and setting a temperature. While these methods are often treated differently at the logits level, they can all be simplified into standard sampling from an adjusted probability distribution. For instance, argmax sampling can be likened to nullifying all non-max elements of the distribution and then normalizing it. This way, we can handle all types of sampling within a standard framework. We'll assume that P, X, and Q, X, are the distributions from two models, M_P and M_Q, adjusted for the sampling method. 2.3 Speculative Sampling. Instead of sampling XSIMP, X, we sample XSIMQ, X. If Q, X, is less than or equal to P, X, we keep it. If Q, X, is greater than P, X, we reject the sample with a probability of 1 minus the ratio of P, X, to Q, X, and sample X again from an adjusted distribution. It's easy to show that for any distributions P, X, and Q, X, and X sampled in this way, indeed XSIMP, X, we can sample a token X_1, sim Q, X, calculate the distribution P, X, and speculatively calculate the distribution of the next token X_2. If X_1 is rejected, we discard the computation of X_2 and resample X_1 from an adjusted distribution. If X_1 is accepted, we keep both tokens. This idea can be generalized to sample between 1 and gamma plus 1 tokens at once. 3.1 Number of generated tokens. Let's analyze the reduction factor in the number of serial calls to the target model, or equivalently, the expected number of tokens produced by a single run. The acceptance rate beta_x_ less than t, given a prefix x_ less than t, is the probability of accepting x_t, sim q, x_t, x_ less than t, by speculative sampling. E, beta, is a measure of how well M_q approximates M_p. If we assume that the betas are independent and identically distributed, and denote alpha equals E, beta, then the number of tokens produced by a single run is a capped geometric variable, with success probability 1 alpha and cap gamma plus 1. The expected number of tokens generated satisfies a certain condition. 3.2 Calculating alpha. We can derive a simple formula for calculating alpha given a prefix and the two models M_p and M_q. We start by defining a natural divergence D_LK. This divergence is a symmetric divergence in 0, 1. D_LK, P, Q, equals 0 if P equals Q, and equals 1 if P and Q have disjoint support. The acceptance rate beta equals 1 minus D_LK, P, Q. Finally, alpha equals 1 minus the expected value of D_LK, P, Q, or the expected value of the minimum of P and Q. This is confirmed by empirically observed alpha values in our experiments. Section Summary. The section discusses standardized sampling methods and how they can be cast into standard sampling from an adjusted probability distribution. It also introduces speculative sampling, where samples are rejected or accepted based on the probability ratio between the distributions. The reduction factor in the number of tokens produced by a single run of the model is analyzed, and a formula for calculating the acceptance rate alpha is derived based on the divergence between the distributions. Section 3.3 Wall Time Improvement. Let's delve into the topic of improving wall time. We've demonstrated that our algorithm, under the assumption of independent and identically distributed I.D. data, can reduce the number of times we need to call our target model. This reduction is by a factor that can be described as the difference between 1 and alpha raised to the power of gamma plus 1, all divided by the difference between 1 and alpha. Speculative execution, a key feature of our algorithm, assumes that we have sufficient computational resources to handle the increased concurrency. For our wall time analysis, we'll assume that we can run gamma plus 1 concurrent evaluations of our target model, denoted as m_p, in parallel without increasing the wall time. To calculate the total improvement in wall time, we need to consider the cost of running the approximation model, denoted as m_q. We define a cost coefficient, c, which is the ratio of the time it takes to run m_q once to the time it takes to run m_p once. Unlike alpha, which is an inherent property of the models and the task, the value of c depends on the hardware setup and software implementation details. In our experiments, where m_q is typically much smaller than m_p, c was always less than 0.05 and often almost 0. We propose a theorem that the expected improvement factor in total wall time is the difference between 1 and alpha raised to the power of gamma plus 1, divided by the product of the difference between 1 and alpha, and the sum of gamma times c in 1. To prove this, let's denote the cost of running a single step of m_p as t. Each run of our algorithm costs t times the sum of c times gamma and 1. For running the approximation model m_q gamma times and running m_p once. According to our theorem, this produces an average number of tokens equal to the difference between 1 and alpha raised to the power of gamma plus 1, divided by the difference between 1 and alpha. So, the overall expected cost for producing a token with our algorithm is the product of t and the sum of c times gamma and 1, all divided by the difference between 1 and alpha raised to the power of gamma plus 1. Since the cost of producing a single token with the standard decoding algorithm is t, we get the desired result. Our theorem assumes long enough generations. For example, since we run m_p at least once, the improvement factor is limited by the number of generated tokens. We also propose a corollary. If alpha is greater than c, there exists a gamma for which we'll see an improvement, and the improvement factor will be at least the sum of 1 and alpha, divided by the sum of 1 and c. Now, let's discuss the number of arithmetic operations. Our algorithm runs gamma plus 1 instances of m_p in parallel, so the number of concurrent arithmetic operations increases by a factor of gamma plus 1. Since our algorithm produces at most gamma plus 1 tokens per run, the total number of arithmetic operations might be higher than that of the standard decoding algorithm. When we accept the sample from m_q, the increased concurrency is free, and the total number of operations isn't increased. However, when we reject a guess, computation is wasted. Let's define c as the ratio of arithmetic operations per token of the approximation model m_q to that of the target model m_p. We propose a theorem that the expected factor of increase in the total number of operations of our algorithm is the product of the difference between 1 and alpha, and the sum of gamma times c and gamma plus 1, all divided by the difference between 1 and alpha raised to the power of gamma plus 1. To prove this, let's denote by t the number of arithmetic operations done by a standard decoding baseline per token, i.e., the number of operations of a single run of m_p. Then a single iteration of our algorithm costs t times the sum of c times gamma and gamma plus 1 operations, for gamma runs of m_q and gamma plus 1 parallel runs of m_p. Dividing by the expected number of tokens produced by our algorithm, and by t, we get the desired result. If alpha is low, the increase in the number of arithmetic operations is high, and vice versa. For transformer decoders, the total number of arithmetic operations by our algorithm, not counting runs of m_q, can be bounded from above by a single run of the same size transformer encoder. Unlike the total number of arithmetic operations, the total number of memory accesses can decrease with our method. Specifically, the target model's weights and KV cache can be read once per execution of our algorithm, so the number of memory accesses for reading them shrinks by a factor that can be described as the difference between 1 and alpha raised to the power of gamma plus 1, divided by the difference between 1 and alpha. Section summary. The authors demonstrate that their algorithm significantly reduces the number of calls to the target model by a factor of 1 alpha caret gamma plus 1, 1 alpha, assuming the d assumption. However, it is important to note that this improvement relies on having sufficient compute resources to support increased concurrency. Additionally, the expected improvement factor in total wall time is 1 alpha caret gamma plus 1 alpha gamma c plus 1, where c represents the cost coefficient. Section 3.5 Choosing gamma. In this section, we're discussing how to choose the optimal value for a parameter we'll call gamma. Given two other parameters, c and alpha, and assuming we have enough computational resources, the best gamma is the one that maximizes the equation for improving processing time. This equation is essentially the ratio of 1 minus alpha raised to the power of gamma plus 1 to 1 minus alpha times gamma times c plus 1. Since gamma is an integer, we can find the optimal value numerically. We illustrate the trade-off between processing speed and the total number of calculations for different values of alpha and gamma, assuming c equals a constant value. We also show a simplified diagram to help visualize this. Instead of choosing a single value for gamma based on alpha, we could further improve our results by predicting the value of another parameter, beta, and adjusting the value of gamma accordingly during the run. If we had a perfect predictor for gamma, we could expect the number of generated tokens to be 1 divided by 1 minus alpha. For typical values of c and alpha, and assuming unlimited computational resources, this could lead to a processing time improvement factor up to about 60% higher than the improvement factor with a fixed gamma. We're leaving further exploration of this idea for future work. We also discuss approximation models, which are used in speculative sampling and decoding. These models guarantee the same output distribution for any choice of approximation model without restriction. In our experiments, we mostly tested smaller transformers as the approximation models. We found that choosing an approximation model that's about 2 orders of magnitude smaller than the target model usually performed best. We also discuss negligible cost models, which are approximation models with a negligible cost relative to the target model. In this case, we get an expected processing time improvement that's bounded from above by 1 divided by 1 minus alpha. One interesting type of negligible cost approximation models are n-gram models, where the evaluation amounts to a table lookup. We also tested other simple heuristics as negligible cost approximation models. For example, in cases where long sequences are likely to repeat, an approximation model that simply copies tokens from the context might yield high values of alpha. These parameter-less approximation models have the advantage of being even simpler to deploy from a production standpoint. We also discuss non-autoregressive models, which can be used by speculative decoding. Then, instead of the autoregressive loop, we just call the non-autoregressive model once. We then discuss our empirical results. We implemented our algorithm and compared it to the implementation in the T5X codebase for accelerating T5XXL. We tested a standard encoder-decoder T5 version 1.1 model on 2 tasks: English to German translation and text summarization. For both tasks, we used T5XXL for the target model. For the approximation model, we tested several existing configurations. We found that T5 small, with a good balance of C and alpha, provides the highest speedup out of the tested approximation models. As expected, alpha increases with the size of the approximation model. Interestingly, alpha and processing time improvement are higher for argmax sampling. We observed speedups of up to 3.4 times on the translation task and slightly lower speedups for the summarization task. These empirical results match well with the theoretical predictions, with some variance due to implementation details. Section summary. The authors discuss the process of choosing the optimal value for gamma in order to maximize the wall time improvement equation. They also explore the use of approximation models, such as smaller transformers or negligible cost models, to further enhance the inference speed. Empirical results show that T5 small, 77M, provides the highest speedup among the tested approximation models, with observed speedups of 2.6x to 3.4x on the translation task and 2.3x to 3.1x on the summarization task. Section 4.2 Empirical Alpha Values. We've been working on a method that we've only implemented for the T5 model so far, but we've also measured alpha values for a variety of tasks, sampling methods, target models, M_P, and approximation models, M_P. To do this, we evaluated the expectation from 10,000 tokens generated by M_P for each setting. We tested a GPT-like model with 97 million parameters for unconditional language generation. This model uses a transformer decoder with JLU activations. For the approximation model, we experimented with a transformer decoder model with 6 million parameters, as well as simple unigram and bigram models. The target model has 97 million parameters. We used BERT tokenization with 8,000 tokens for all models. We also tested a lambda model with 137 billion parameters on a dialogue task. We used existing checkpoints from lambda 137b as the target model and lambda 8b, lambda 2b, and lambda 100m for the approximation models. Our observations showed that approximation models that are significantly smaller than the target model tend to produce alpha values between 0.5 and 0.9. Interestingly, we also found that the sharper the adjusted distribution, the higher the alpha values. Even simple unigram and bigram approximations yield significant alpha values. For instance, in the case of English to German translation, the bigram model has an alpha value of 0.2, which surprisingly leads to a 1.25 times speed improvement. There has been a lot of research on improving the efficiency of inference from large models. Many approaches aim to speed up inference from large models in general, and autoregressive models like transformers in particular. Some methods try to make inference more efficient for all tokens, such as distillation, sparsification, quantization, and architecture modification. Other methods adapt the amount of computation to problem difficulty, like attending to a subset of the inputs and early exits. Our approach is similar to adaptive computation methods, but it uses a heuristic to determine when to stop, losing the guarantee of identical outputs to those of the target models. These methods usually save on both inference time and arithmetic operations, but require a change of architecture, a change of training procedure, and training custom models or retraining of existing models. They usually also change the outputs of the model. We've presented speculative sampling, which enables efficient stochastic speculative execution. We've analyzed its impact on decoding from autoregressive models like transformers via speculative decoding and have shown that given enough compute resources, we get meaningful 2 to 3 times speedups in practice versus T5x, a popular optimized implementation. One limitation of speculative execution in general, and of speculative decoding in particular, is that latency is improved through increased concurrency at the cost of an increased number of arithmetic operations. Thus, our method is not helpful for configurations where additional computation resources are not available. However, in common cases where additional computation resources are available, our method provides the speedup with significant benefits. The model architecture doesn't change, retraining isn't required, and most importantly, the output distribution is guaranteed to stay the same. Our method is easy to implement, and can be used to speed up inference using out-of-the-box models without developing and evaluating custom schemes. There are several directions for follow-up research, such as further investigating the compatibility of speculative decoding with beam search, exploring a hierarchical version of the algorithm, varying the approximation model and the number of guesses during inference, and testing speculative decoding in other domains like images. Finally, we note that stochastic speculative execution and speculative sampling can be helpful outside the scope of speculative decoding from autoregressive models. For example, given two slow functions, f, x, and g, y, such that f, x, generates a distribution from which g's input is sampled, we could use our method to run f and g in parallel. This setup might arise in physics simulations, or in reinforcement learning where f is a large model that produces a distribution on actions, and g is the world simulation, which would be interesting to explore.